All right, let's just dive right into this explainer. Today, we're taking a simple page from your textbook, specifically Activity 7.1 right there on page 195, and we're going to transform it into a full-blown virtual laboratory experience. We're taking those kind of abstract concepts of acids and bases and making them highly visual and, honestly, incredibly practical.
I mean, imagine standing in front of a lineup of identical, perfectly clear liquids on a lab bench. How do you tell the harmless ones, like, say, weak vinegar, from the really dangerous concentrated laboratory acids? You definitely can't touch or smell them, right? Relying on your basic senses in chemistry is a huge no-go. So we need a way to force these chemicals to literally reveal their true identities to us visually. And honestly, that's exactly the puzzle we're solving today. To do this, we're going to methodically solve this problem in 5 steps. We'll hit the acid-base mystery, meet the indicators, set up Activity 7.1, decode the color changes, and wrap up with the limits of indicators. So let's kick things off with Section 1, the acid-base mystery, where we identify our suspects. Now, Activity 7.1 is our exact blueprint for this whole experiment, the identification of acids and bases by indicators. It literally gives us everything we need to run a comprehensive diagnostic test on an array of completely unknown liquids. And here are our raw materials. These are the suspects in our little mystery. It's actually a pretty fascinating mix. We've got everyday household items you probably have in your kitchen right now, like lime juice, vinegar, maybe some soap solution. But we've also got some heavy-hitting lab chemicals in the mix: dilute hydrochloric acid, dilute sulfuric acid, and dilute sodium hydroxide. To the naked eye, they all look suspiciously similar. So our mission is to sort them out into their proper scientific categories. Moving right along into Section 2, meet the indicators. Time to check out our chemical tools. We're going to use 4 highly specific chemical indicators to force our suspects to talk. We've got blue litmus and red litmus. Those are just small strips of paper, alongside methyl orange and phenolphthalein, which come as liquid drops. Now, each of these has a really specific reaction profile when you drop them into different chemical environments. So if we drop these into our unknown solutions, what do you actually expect to happen? Well, by definition, an indicator is just a substance used to approximately identify a solution as an acid or a base, just by observing a specific color change. Think of them like chemical informants. When they run into an acid, they wear one disguise, but the second they hit a base, boom, they instantly change into another. All right, on to Section 3, setting up Activity 7.1. Let's look at the actual procedure. If we distill that dense paragraph of instructions from page 195, we get these 3 super clean, actionable lab steps. First up, we gather our 6 specific solutions into separate test tubes. Second, we systematically add our 4 different indicators to samples of each. And third, arguably the most important step for any scientist, we carefully record what we see. And that brings us to this massive grid, which represents all the data we're about to collect. I mean, just think about the scope here. We've got 6 unique solutions on the left, and we're testing every single one against our indicators across the top. We're effectively running dozens of little micro-experiments. Every single blank space you see here is a chemical reaction just waiting to happen. Now for Section 4, decoding the color changes. Let's translate that data. Okay, here it is, our ultimate decoder key. This is how we categorize every single reaction we just witnessed, and honestly, it's the absolute secret to unlocking this entire activity. It tells us exactly which color means acid and which means base for every single indicator we threw at them. Using that key, we can see litmus gives us this really stark, contrasting visual cue. If you take blue litmus paper and dip it into our dilute hydrochloric acid, it instantly flushes this vibrant red. But if you take red litmus and dip it into, say, the soap solution, which is a base, it turns a brilliant blue. It's just a fantastic, immediate binary test. Red means acid, blue means base. Simple as that. Then you have phenolphthalein, which acts almost like magic. If you drop it into an acidic environment, like the lime juice or the vinegar, literally nothing happens. It stays completely colorless. But the very second you drop it into a basic environment, like our dilute sodium hydroxide, it flashes this bright, striking pink. It's an incredibly dramatic visual confirmation of a base. You really can't miss it. And for our final indicator, methyl orange. This one really builds our confidence by shifting from red in acids to yellow in bases. So if our earlier test hinted that a substance was an acid, Adding methyl orange and watching it turn a deep red just totally confirms it. If it's a base, it turns this bright, sunny yellow. By cross-referencing all of these color shifts, we can sort that initial lineup of 6 suspect liquids with absolute 100% confidence. Which brings us to our final section, Section 5, the limits of indicators. Because yes, there are limits.
Your textbook specifically warns us about this. This method is really just an approximation. Now, don't get me wrong, our indicators did a wonderful job separating the acids from the bases. But as an overall identification method, it's kind of lacking in accuracy. It tells us what a substance is, it says, yep, this is an acid, but it totally fails to tell us how strong it is. Like, weak vinegar turns litmus red, sure, but so does highly corrosive, dangerous sulfuric acid. So obviously we need something a bit more precise. And that's exactly where the pH scale comes in. It's the ultimate tool that solves this exact limitation. While the basic indicators from our activity just gave us broad categories, the pH scale gives us a precise numerical value from 0 to 14. Right in the middle, 7 is totally neutral. Think pure water. Anything lower than 7 is acidic, and it gets stronger the closer it gets to 0. On the flip side, anything higher than 7 is basic, getting stronger all the way up to 14.
So we started off by turning invisible properties into bright, colorful signals, right? We successfully decoded the nature of our 6 suspect solutions using Activity 7.1. But as we've seen, just knowing if something is an acid or a base is really only the first step. So as we wrap up this explainer, I want to leave you with this. If basic indicators only give us a piece of the puzzle, how might measuring the exact chemical strength on the pH scale change the way you see the everyday things around you? From the foods you eat to the actual rain falling from the sky. Think about it. Until next time, keep questioning the world around you.